Hello, everyone. My name is Kevin, and I'm the Director of Product Management at Unchained Labs. I'll be your moderator, and I want to thank you for joining us today. We'll have a Q&A session at the end of today's presentation. So to ask questions, all you have to do is click on the Q&A button at the top or bottom of your screen in the Zoom navigation bar. Type in your question, and we'll get to as many of them as we can. If we run out of time, it's really helpful if you do not click the anonymous box, because that way we can follow up with you after the presentation, still get you the answers that you need. And now I'd like to introduce Brian Haldeman, Product Manager for Stunner. Today, Brian will take us through Stunner's unique ability to characterize antibodies and biologics for concentration, size, and aggregation. We'll check out a few use cases on evaluating antibodies and different formulations, including a method that opens the door to screening different formulation options with low sample volumes and high throughput. And now I'll hand it over to Brian. Brian, floor is all yours.
Great. Thanks, Kevin. Really appreciate it. And thank you, everybody, for joining. Today, I'm going to talk to you guys about how to get to know your perfect antibody formulation with Stunner. So I live in the Sierra Nevada mountains, where the weather can be super unpredictable. We love to bring our dogs out wherever we go, but it's important to keep them comfortable when the weather doesn't want to cooperate. For example, our friend Charlie here, who's wearing his favorite winter jacket. So Charlie's an English bulldog, and for those of you who are familiar with the breed, you know they can be super temperamental. If Charlie's not comfortable, he's going to let you know. So just like Charlie, who needs his winter coat, our antibodies also need the perfect formulation buffer to be comfortable in their environment. So also just like Charlie, our antibodies, if they're not comfortable in their environment, they're going to let you know. So the right buffer really keeps mAbs in their comfortable environment, right? So by having the right buffer, our mAbs are going to remain monodisperse. They're going to remain developable. So when the temperature goes down or the concentration goes up for therapeutic dosing, they're going to remain in their monodisperse functional state. Now, on the other hand, if you have the wrong buffer, your antibodies are going to have more interaction with themselves. So we're going to see more interactions with more aggregation. They're going to be more unstable. And this is going to be problematic when developing a therapeutic. So when you are developing a therapeutic, you really have a few questions that you need to have answered. And these typically require different types of technologies to be able to address those questions. So for example, how much do you have? For measuring concentration, we're usually going to use a system with UV-Vis, something like that. And also, you want to know if you have aggregates in your sample. What's the quality of your sample with regards to size? And for that, we're going to utilize a system that utilizes DLS, or dynamic light scattering. Today, I'm going to introduce you to a system called Stunner, which combines both of those technologies into a single platform. So with Stunner, you can do protein concentration and protein quant. You can look at the size and polydispersity of your samples, and you can measure colloidal stability, or B22 and KD, all from just 2 microliters of sample. So when we load our samples into the Stunner plate, we only require 2 microliters of sample with no dilutions and no reagents required. Just simply load your samples into the plate, which has 96 individual microfluidic circuits that, so with just 2 microliters of sample, we are able to measure both UV-Vis concentration and sizing data. So if we measure an entire plate of 96 samples, we can do concentration measurements in just about 10 minutes. And if you want to tack on DLS sizing as well, we can do an entire plate in about 1 hour. So here, with the help of some fluorescein and a black light, we can see what those individual microfluidic circuits look like. So we have 2 circuits that are loaded here. And if we load a third one here as well, we will be able to see, once we add those 2 microliters of sample, we can then put that into the input well, and that will extend to that microfluidic circuit in just a matter of seconds. So not only is Stunner super easy to use, but the data that you get from it is super quantitative as well. So what we're looking at here is the dilution series of an IgG, showing that we can measure everything from 275 OD down to 0.03 OD. So we have this huge dynamic range that we can measure through. And so because of that, we don't need to make dilutions of our sample to be able to measure them on Stunner. So with this dilution series, we're showing the UV spectra, and we have that OD peak right about 280 nanometers, and that allows us to determine our protein concentration. When we look at that OD and we plot that against the known IgG concentration, we have this linear relationship both at the top and the bottom of that range that we're measuring. You'll also notice that each one of these data points has multiple replicates, just to show that our data is also extremely reproducible as well. So just to go into a little bit more detail with that, if we're plotting here the known concentration compared to the measured concentration on Stunner, we show that we have a linear relationship between 200 mg per mil down to 2 mg per mil. So accuracy is within 2% during that entire range that we're measuring, and precision between replicates is within 1%. And that is due to the fact that we have two fixed path length cuvettes within each one of those microfluidic circuits. And that allows us to measure both high concentrations and low concentrations very accurately and with precision as well. So another really cool thing that Stunner can do is to unmix what we have in our sample. So for example, if we were looking at just this UV spectra that we see here, a traditional UV-Vis spec would take that absorbance at 280 nanometers and determine our protein concentration from there. The problem with this is there are different contaminants that can contribute to that absorbance at 280. So whether it is nucleic acids, whether it is turbidity or cloudiness in our sample, all of these can contribute to that absorbance at 280 and lead to some inaccurate measurements if you're just reading directly from that UV-Vis spectrum. So what Stunner is able to do is to deconvolute that spectrum into individual components to be able to look at the quality of your sample here, to be able to identify if you have any impurities present or if we have turbidity in our sample as well. So the first example here, Stunner is showing that we are able to deconvolute this sample, showing that we do have impurities shown in blue. So with black, we have the entire UV spectrum shown here. Green is our protein contribution, and then blue is showing our contaminants that are present in that sample. You notice that our contaminants have a signature peak right here at 260 nanometers. So that suggests that our sample is contaminated with nucleic acid. And basically, we need to go through further processing or purification in order to further characterize the sample. Stunner is also able to see through turbidity or cloudiness in our sample. So the cloudiness that's present here is shown with this light gray line, and we can see that the turbidity in our sample is actually above where we're measuring for absorbance, and we're able to very accurately still determine that absorbance from our protein contribution there as well. So turbidity can be from anything in our samples from lipid contamination to bead carryover from a purification step to aggregates present in the sample. All of those can contribute to turbidity, but Stunner is able to see through that to accurately determine our protein concentration, even when we have turbidity. So next, we really wanted to push the limits of Stunner's capabilities. So in this case, we really wanted to show how precise our measurements can be for both quant and sizing. And the way that we did this was by running 8 replicate measurements of an IgG. Both concentration and sizing results are shown here. So for concentration, we measured concentration right around 10 mg per mil. But I think what's really important here is that CV that we measured between those 8 replicates is only 0.2%. So we're super precise when it comes to measuring concentration. And we could say the same thing for sizing as well. So between those 8 replicates, we have a Z-average diameter right around 11 nanometers, which is what we would expect for a typical IgG. And we have a CV of just about 1.5% between those different replicates. So now to dive a little bit further into the sizing measurements that we can get on Stunner. So in this case, we're looking at 2 commercially available protein standards that are different sizes, both ovalbumin, the smaller of the 2 in green, and the larger of the 2, thyroglobulin, in blue. These were both run on independent measurements, and then the results are overlaid here. What I want to draw attention to is that the larger of the 2 particles, thyroglobulin, is scattering more light. So both of these proteins were loaded at the same concentration, but we can see the larger of the 2, the peak height is much higher for this one. And this is simply because when measuring light scattering, larger particles are going to scatter more light. Just to show over here with the mass distribution, we can confirm that both of these proteins were loaded at the same concentration. But once again, larger particle, it did scatter more light. And we can use that to our advantage when it comes to detecting aggregates within our samples. So for aggregates, we have two different samples that we measured here, one of which was a totally monodispersed MAB over here on the left. And then on the right, we have a sample that was primarily monodispersed MAB that was spiked in with 1% aggregates. Now I want to show that, with our intensity distribution here in green, we would expect for our completely monodispersed sample to have that single peak right around 10 nanometers. But our sample that was primarily monodispersed, but with that 1% aggregates, we see these large peaks right around 500 nanometers. That signifies that we have aggregates within that sample. Now, keep in mind that the relative amount of aggregate is very small here, but since we know that larger particles scatter more light, we can use Stunner as a super sensitive aggregate detector to let us know when we do have aggregation present in our sample, even when it is a very low amount of aggregation present. And just to confirm that with the mass distribution shown down here below, once again, we have that monodispersed peak for our 100% MAB sample. And with our sample that was spiked with 1% aggregates, we have that monodispersed peak here. But our aggregate peak with the mass distribution is just basically a blip on the radar. So it's a very low amount of aggregate that's physically present, but it does scatter a ton of light. So we're able to see that in the intensity distribution above. I also want to note here that Stunner can seamlessly integrate with different liquid handlers or robots for loading plates into the Stunner. We do have an API software available to be able to integrate Stunner into your robotics workflow to really crank up that throughput to higher levels. So for today's experiment that I want to show, this is a study that we did where we looked at 4 different antibodies, 2 of which are FDA-approved therapies, both adalimumab and trastuzumab, and we wanted to do an excipient screen on these. So what we did is we exchanged them all into different formulation buffers. It was actually the same buffer components, a histidine and pH 6 with tween 80, but then we varied the excipient that was present in those. So we did sodium chloride, sucrose, arginine, or a combination of sucrose and arginine together. So to do the buffer exchange for these experiments, we utilized our automated buffer exchange system called Unagi. So Unagi is super flexible when it comes to sample throughput. We can do up to 8 samples. For volumes that we can measure within, volumes that we can exchange within the system, we can do anything from about 0.5 ml up to 8 mils. And all of this requires less than 15 minutes of hands-on time to set up that experiment. And once you hit start, you can let Unagi work its magic. So the magic inside of Unagi is a pressure-based buffer exchange shown here. This is the workflow that we utilize for buffer exchange. So we can start here on the left with inputting our samples. Samples go into our consumable that we call an UNA that you see here. And the UNA itself has a filter at the bottom that has a specific molecular weight cutoff. You can choose which one you want to use for molecular weight cutoff, also for chemistry. So which filter is going to be most appropriate for your sample. You can go ahead and choose that. Followed by, we can, once you put the sample inside of the Unagi, we can then measure the volume utilizing an ultrasonic volume sensor. So once we measure that volume, we can then apply pressure and mixing, and that will allow the filtrate to go through the bottom of that filter, keeping our sample inside of the UNA. After a certain pressurization time, we can then go back and measure that volume again and refill with the buffer that we want to exchange into. So this is an iterative process, and it's a cycle that's going to continue until you reach that target percent exchange, which we defined in the software before we started our experiment. So once we have our exchange sample, we then have the option to concentrate that. So if your sample is fairly dilute, we can concentrate it before doing additional characterization studies. So one key differentiator with Unagi compared to other methods for buffer exchange is the fact that we apply this orbital mixing when we do pressurization. So other methods for buffer exchange, such as Amicon filters inside of a centrifuge, utilize something called dead-end filtration. And one of the issues with that is that our sample tends to build up against that filter, and that leads to super inefficient buffer exchange. So while we apply pressure and when we're doing our buffer exchange, we utilize orbital mixing to keep that sample homogeneous, to keep it from building up against that filter, and that leads to more efficient buffer exchange. So let's dive back into some Stunner results. So, after we buffer exchanged our samples, we then wanted to check the quality on Stunner of each one of those. So what we're looking at here is our 4 different MABs along the x-axis with bars signifying each one of the different formulations that we had for each one. Along the y-axis on the left side, we have the hydrodynamic diameter or size that we measured. And along the y-axis on the right side is called PDI or polydispersity index. We're going to get into that in a couple more slides, but first I want to focus on the size that we measured. So that is signified by the different bars here, and we can see that we have one clear outlier here, and that is adalimumab in the presence of sucrose, so this blue bar that we see there. So the rest of these samples were right along the size that we would expect them to be, just about 10 nanometers, and that's the threshold that we put here with this dotted line. So let's dig into a little bit further as to why we have this sample that has an increased average size with adalimumab in the presence of sucrose. And to do that, we can look at the direct result or the direct output from Stunner with that intensity profile. And what we're looking at here is basically the first red flag that we can determine that our antibody is not happy in this formulation. So of course we have that one population here right around 10 nanometers that we would expect. But along with that, we have two larger size populations that are present within that sample. And that signifies that we do have aggregation present. Now, what we can conclude from this is that this formulation buffer is really not appropriate for this specific mAb, and we can then exclude it from any additional characterizations that we're going to do. So diving back into those results, I now want to focus on the y-axis on the right side, which is PDI, or polydispersity index. So PDI measures basically the range of sizes that we're able to measure under each one of these conditions. So the lower the PDI, the better. So typically we have PDIs below 0.1, we consider monodisperse. So we have that dotted line as a threshold here to show that anything below that dotted line is a monodispersed sample. Anything above 0.1, we would typically consider a polydispersed sample. You notice that a lot of these dots, which are showing our PDI for each one of these conditions, are above that threshold. And if you look at that a little bit closer, we can see the trend here that it's basically samples that are in the presence of sucrose, either sucrose by itself or sucrose and arginine, that are above that threshold. And we can look at that in a little bit more detail when it comes to the results from Stunner as well, to try to explain why that's happening, so whether that's due to aggregation or if there's another reason for it. So to help explain what we saw there with higher PDIs with samples in the presence of sucrose, we're looking at two different conditions here, with mAb1 in the presence of sodium chloride and mAb1 in the presence of sucrose. So both of these, we can conclude that our antibodies are actually not aggregating, but the source of that higher PDI for samples in the presence of sucrose is the signature peak that we see down here at 0.8 nanometers. So that peak was present in all of our samples that contain sucrose, and it's basically due to the fact that that buffer component was being detected by the DLS detector, and that is the source of the high PDI. So what we can conclude from this is, since we don't have aggregation with these, we can continue on characterizing those samples to find the ideal formulation buffer, even when that PDI was a little bit higher than the threshold we'd like to see at 0.1. So the next step that we wanted to look at with these was to measure colloidal stability. And what colloidal stability tells us is whether or not these samples are prone to aggregation in that specific buffer that we chose. So when we're looking at colloidal stability, we measure two different parameters, both B22 and KD. And for these, if we look along the x-axis, we're basically going to do a dilution series of our protein, and we are going to look at two different outputs from DLS along that dilution series. So for B22, we're going to measure Kc over R on the y-axis. And then for Kd, we're going to measure the diffusion coefficient along that dilution series. So what we're looking for with colloidal stability is the trend over those dilutions that we made. So generally, positive slopes are going to indicate that our samples are not aggregating and they're not prone to aggregation. But negative slopes, that's another red flag that we need to look out for, that our samples are prone to aggregation. So tying that back to our formulation screen that we did, one example that I wanted to show here was we can conclude that mAb1 is happy in the presence of just plain sucrose by itself. So we're looking once again at KD and B22, and two different conditions that we're looking at here. So sucrose in blue and sucrose and arginine in yellow. What we can see for both KD and B22 is that we have that positive slope just for our samples that contain sucrose. So that's a good thing. That's what we want to see. But when we add arginine into that, that basically negates any of the positive effects from just the sucrose by itself. And we see either a slightly negative slope or a flat slope shown here. Now, like I said before, we are really looking for those positive slopes, and that helps us determine which is the ideal formulation buffer. So in this case, we can confirm that mAb1, the ideal formulation buffer, is just sucrose by itself. So concluding all of these results together into one graph shown here, we can see that each one of these mAbs is really picky for the right buffer. It's really difficult to predict which is going to be the right formulation buffer for each individual mAb without directly testing it. So Stunner is an excellent tool to be able to measure these directly in an efficient and low volume manner. So what we're looking at here is each one of our constructs in each one of the different formulation buffers. And highlighted in green is the conditions that have the most positive slope. So what this would define as the ideal formulation buffer for that specific mAb. Now, we can see that both mAb1 and trastuzumab preferred sucrose by itself. mAb2 preferred sucrose and arginine together. And then our problem child for this study, adalimumab, really didn't prefer any of these buffers. So there really was not an ideal buffer formulation for adalimumab. So what that tells us, we need to go back to the drawing board, choose some different formulation buffers, and find which one is ideal for adalimumab itself. So in this study, we showcased how Stunner is the ultimate antibody characterization tool to find the best formulations for your antibody. Stunner can combine both UV-Vis and DLS to enable users to get concentration, size, and monitor for aggregation in up to 96 samples at one time. Stunner takes that formulation screening to the fast track to find the perfect condition to keep your mAbs comfortable. And with all that time you're saving by using Stunner for your formulation screens, you can find that ideal formulation buffer for your antibody and still have time to find the perfect condition to keep you and your dog both comfortable as well. And with that, I want to thank everybody for joining. I will entertain any questions and hand it back over to Kevin. Thanks, Kevin.
All right, Brian, thank you for taking us through that talk using Stunner to look at two key aspects of biologics, concentration and sizing. It was an interesting walk through how to use both of those approaches to keep an eye on biologic samples and how to apply them to screening formulations, and especially how to use KD-E22 data effectively. So there's been some great questions already submitted by the audience. You can still ask a question out there if you're curious by entering it into the Q&A section of your Zoom navigation bar. So let's get to it. First up here at the top of the list, so what are the minimum and maximum concentrations I need for colloidal stability measurements?
Sure, absolutely. So when I am recommending, when somebody's setting up one of these experiments in their lab, I recommend starting, for example, for an IgG, you want to go from 10 mg per mil down to about 1 or 2 mg per mil. So in that range with 5 or 6 data points in between there.
Okay. And then do you have to use Unmix, the software that we showed during the talk? Do you have to use Unmix for your concentration measurements?
Yeah, good question. While Unmix can be super useful, it's not always relevant to using. You don't have to use Unmix. One thing I really like about Stunner is the fact that you can choose different applications once you've acquired the data, right? So if you wanted to use Unmix and not use it and compare in between, you don't have to run two different samples. You can simply choose a different app to be able to look at what the data looks like with whether or not you apply Unmix.
Okay, that sounds like a good tool for troubleshooting. So we also talked about, beyond Stunner, we talked about Unagi for buffer exchange. So for buffer exchange on Unagi, how long does that take and what's the typical yield for proteins?
Yeah, so Unagi, I think the short answer here is it can vary, right? But when it comes to buffer exchanging an IgG, I think for the most part, people exchange to about 95% exchange. That seems to be pretty standard. And that takes just about an hour to buffer exchange an IgG to 95%. And
Okay.
the typical yield for that, for proteins, we regularly see above 90% for the yield.
Okay. So back to Stunner. Can I run samples other than proteins?
Oh yeah, yeah. So proteins is only one of the hats that Stunner can wear, right, for different capabilities. So Stunner, we develop apps for both LNP quant, for viral vector quant, proteins. There's lots of different things that Stunner can do. We really focused on one today, but yeah, I really recommend people look at the resource page on our website, and that really focuses on some of the other capabilities of Stunner with different webinars, different app notes, things like that.
Okay. And then would this kind of formulation screening workflow work on proteins other than antibodies?
Yeah, yeah, absolutely. So, one consideration that you would have there is maybe that dilution series I spoke about for an IgG between 10 and 1 or 2 mg per mil. You might have to change that depending on the size and the characteristics of your protein, and that's something you can determine iteratively. But yeah, absolutely, it can work for other proteins as well.
Okay. This one's a little tricky, so I'm going to try to interpret it, make sure I get the right answer here. So when we're measuring concentrations on Stunner, we were showing some data looking at proteins that had some contaminants that were likely DNA or RNA. So can you turn off that ability is the first part of it. And the second part of it is, the concern about like how would you measure ADCs because they could also contribute absorbance in that 280 nanometer region.
Sure. Yeah. So to address that first part, I believe that's similar to the question we addressed earlier, where yeah, you have the option to either utilize unmix or not. And when it comes to ADCs, that's something where we could take advantage of that unmix, where we're able to separate out the absorbance from different components that are in our sample, right? So if you have a drug that is absorbing around 280 or would interfere with that protein concentration, we can deconvolute that into both the drug by itself and the antibody by itself as well. So we could still get accurate concentration measurements both for your drug linker for an ADC as well as the antibody itself.
Okay. Yep, makes sense. If you know what the underlying spectrum are, you can kind of do the math. All right, so that gets us to the end of the Q&A list. So thank you for answering all of those questions, Brian, and thank you again for a great presentation. I also want to thank all of you that joined us live today. If you'd like to have a deeper conversation with our team, please do get in touch with us at info@unchainedlabs.com or through our website, unchainedlabs.com. We'd love to connect and talk science with you. Thank you again for attending our virtual webinar or seminar, and have a great rest of your day.
Thank you.